lecture we have seen De Moivre's theorem, the statement of which is for all real values of n cos theta plus I sin theta raised to n equal to cos n theta plus I sin n theta. Also in the last lecture we have seen some examples on De Moivre's theorem. So continuing with the same, we will see some more examples on this De Moivre's theorem. So the first example is using De Moivre's prove that 1 plus sin theta plus I cos theta raised to n divided by 1 plus sin theta minus I cos theta raised to n is equal to cos of n pi by 2 minus n theta plus I sin n pi by 2 minus n theta. So LHS is this one, but here sin theta is equal to cos of pi by 2 minus theta. We take the help of trigonometry. Cos theta is sin of pi by 2 minus theta. So 1 plus sin theta becomes 1 plus cos of pi by 2 minus theta, and cos theta becomes sin of pi by 2 minus theta. Numerator, denominator same except the sign in between. So this one is your LHS. Now use the formula 1 plus cos of pi by 2 minus theta is 2 cos square pi by 4 minus theta by 2. 1 plus cos alpha, that is 2 cos square alpha by 2. So alpha is pi by 2 minus theta. So alpha by 2 means pi by 2 minus theta divided by 2, that becomes pi by 4 minus theta by 2. Also sin alpha is 2 sin alpha by 2 cos alpha by 2. So we take again the help of trigonometry and use these trigonometric results. So this becomes numerator, denominator, they are same except the sign in between. Then from numerator 2 cos of pi by 4 minus theta by 2 is common. Also from denominator 2 cos of pi by 4 minus theta by 2 is common. So that gets cancelled, and what remains? 2 gets cancelled, cos square 1 cos gets cancelled. So cos of pi by 4 minus theta by 2, 2 gets cancelled, cos of pi by 4 minus theta by 2 gets cancelled, and what remains? Sin of pi by 4 minus theta by 2 raised to n, and cos of pi by 4 minus theta by 2 plus I sin of pi by 4 minus theta by 2 raised to minus n. Why? Because our need is the sign in between is plus. So we make it plus and we change the sign of n here, it becomes minus n. Then we use, now we are using the De Moivre's theorem. So cos theta plus I sin theta raised to n, that is cos of n theta plus I sin n theta. So that becomes cos of n cos of pi by 4 minus theta by 2 plus I sin pi by 4 minus theta by 2. First step is this one, n plus n, that is 2n, and then we use our De Moivre. Watch that. This one is raised to n, this one is raised to minus n. So use of log indices n minus minus n, that is 2n, and then we use our De Moivre's. This 2n becomes the multiplying factor here, and ultimately we get our RHS. So this completes the proof of first. Second example is using De Moivre's prove that 1 plus I raised to n plus 1 minus I raised to n is equal to 2 raised to n by 2 plus 1 into cos of n pi by 4. Hence prove that 1 plus I raised to 12 plus 1 minus I raised to 12 is equal to minus 1 to 8. So the particular value of n is putting here, and we are getting the result as 1 plus I raised to 12 plus 1 minus I raised to 12 is equal to minus 1 to 8. So that also we have to prove. First we find the polar form of 1 plus I. So as per our previous knowledge, the polar form of 1 plus I is root 2 into cos of pi by 4 plus I sin pi by 4. Also the polar form of 1 minus I is root 2 into cos of pi by 4 minus I sin pi by 4. I will just remind you how to find polar form. This one is z is 1 plus I, then modulus of z is root of x square plus y square. By that formula it becomes root 2, and alpha is theta, argument is tan of 1, sorry, tan inverse 1 is pi by 4. So cos of pi by 4 plus I sin pi by 4 into root 2, that is the polar form of 1 plus I. Similarly, the polar form of 1 minus I is this one, and therefore our LHS becomes root 2 raised to n into cos of pi by 4 plus I sin pi by 4 raised to n plus root 2 raised to n cos of pi by 4 minus I sin pi by 4 raised to n. So root 2 raised to n is common, and we use our d inverse here also for e. So that is cos n pi by 4 plus I sin n pi by 4 plus cos n pi by 4 minus I sin n pi by 4 sin I sin n pi by 4 and I sin n pi by 4 plus minus, that gets cancelled. Cos of n pi by 4 plus cos of n pi by 4, that becomes 2 times cos of n pi by 4 and root 2 raised to n. So root 2 raised to n means 2 raised to n by 2, and 2 raised to 1 plus 1. Again we use the law of indices. A raised to m into a raised to n is equal to a raised to m plus n. Cos of n pi by 4 as it is, and that is nothing but our RHS. And particular value of n is given, that is 12. If we put n is equal to 12 here, then 2 raised to 12 by 2, 6 plus 1, 2 raised to 7 into cos of 12 by 4, that is 3, cos of 3 pi. But cos of 3 pi is minus 1, and therefore ultimately we are getting this one as 1 plus I raised to 12 plus 1 minus I raised to 12 is equal to minus 128. So that we have proved the result. Next example is again using de Moivre's. Prove that sin of pi by 6 plus I cos of pi by 6 raised to 4 plus sin of pi by 6 plus I cos of pi by 6 raised to 3 is equal to 1 by 2 plus I root 3 by 2. Again we are using the trigonometric result. Sin of theta is cos of pi by 2 minus theta. So sin pi by 6 is cos of pi by 2 minus pi by 6, that is cos of pi by 3. Also cos of pi by 6 is sin of pi by 2 minus pi by 6, that is sin of pi by 3. And therefore our LHS becomes, sin of pi by 6 plus I cos of pi by 6 raised to 4 plus sin of pi by 6 minus I cos of pi by 6 raised to 3. So that is equal to sin pi by 6 is cos pi by 3 plus I sin pi by 3, and cos pi by 3 minus I sin pi by 3 raised to 3 raised to 4 as it is. We use the de Moivre's. This 4 becomes the multiplying factor, cos of 4 pi by 3 plus I sin 4 pi by 3. Here also the same, this 3 becomes the multiplying factor, cos of 3 pi by 3 minus I sin 3 pi by 3. So this cos of 4 pi by 3 is cos of pi plus pi by 3, that is minus cos of pi by 3, and sin of 4 pi by 3 is sin of pi plus pi by 3, that is minus sin of pi by 3. So we put the values of cos of 4 pi by 3 as minus cos of pi by 3, and I sin 4 pi by 3 as minus sin pi by 3, and cos 3 pi by 3 means cos pi, and minus I sin pi is 0, cos pi is minus 1. So we put the values of cos pi and sin pi here. So this becomes minus 1, minus we take it out, and this minus becomes plus. So ultimately we are getting the LHS as cos pi by 3 plus I sin pi by 3. But what is cos pi by 3? That is half. Sin pi by 3 is root 3 by 2, and this is nothing but our RHS. So we have proved the result. The next and the last example is to prove the trigonometric result using de Moivre's. So we have studied these results in our first semester. Cos 3 theta is 4 cos cube theta minus 3 cos theta, and sin 3 theta is 3 sin theta minus 4 sin cube theta. So we take the help of De Moivre's. Cos 3 theta plus I sin 3 theta means cos theta plus I sin theta raised to 3. So this multiplying factor we take it in terms of power. So then cos theta plus I sin theta raised to 3 is cos cube theta plus 3 cos square theta into I sin theta plus 3 cos theta into I square sin square theta plus I cube sin cube theta. So this becomes cos cube theta minus 3 cos theta sin square theta. The term free from I we combine in one bracket, and the term with I we combine in another bracket. So the term free from I from here are cos cube theta minus 3 cos theta sin square theta, and the term with I are 3 cos square theta sin theta minus sin cube theta. Then we compare the real and imaginary parts of both. So cos 3 theta is the real part here, and first bracket is the real part here. So cos 3 theta is cos cube theta minus 3 cos theta sin square theta. So that simplification gives cos cube theta minus 3 cos theta sin square theta is 1 minus cos square theta. So that becomes 4 cos cube theta minus 3 cos theta. And sin 3 theta is the second bracket, 3 cos square theta sin theta minus sin cube theta. But cos square theta again we put 1 minus sin square theta into sin theta minus sin cube theta. So 3 sin theta is minus 4 sin cube theta. After simplification we get this. So hence these two trigonometric results also we have proved with the help of De Moivre's theorem. So De Moivre's theorem is very important theorem, and the examples are so simple, one can get out in your test examination or in your final examination also. So thank you. Stay home, stay safe.